So I got another video for you, and we're on to the last technique of how to solve systems of linear equations. And it's an important one. In fact, we kind of dovetail on this when we get to Gaussian-Jordan elimination in like finite math and stuff like that, where we eliminate variables as we go. That's way down the road. But it all starts right here with another way on how to solve systems of linear equations. So if you remember from the last few videos, we've been talking about systems. And what systems mean are two. So these two linear equations, that means lines, that cross somewhere. If they have a solution, they do. And we're finding the point where they cross. And we have a lot of applications for that. So one way that we've already talked about how to solve this is with graphing. Kind of inefficient because we're going to spend a whole long time graphing, and what if our graph's not perfect? And we're going to kind of have to guess at where the point of intersection is. Then we have to plug in that point into both of our equations to make sure that we actually have a solution to both lines and not just accidentally one. Then we moved on to something much more elegant. We moved on to the substitution method, and it was fantastic. If one of the equations is solved for a variable, it's really nice because we can just plug that variable, substitute it in to the other equation, and it solves nicely. That was the last video. Now we go on to the last technique. Now, a lot of people ask, why do you have two techniques? Why are math teachers always trying to make it harder on me? Well, we're not. We're actually trying to make it easier. So depending on the type of system you have, this is going to dictate what the best practice is for solving it. You see, if you have a system of linear equations where one of your equations, at least one, is solved for a variable, substitution method works great. But if you don't, if you have a system of equations where you're not solved for any variable, elimination method can be your best friend. So we're going to check that out. We're going to look at how it works. We'll spend some time doing about probably 3 examples to make sure that you really understand the concept. And then we'll start building this idea out in some future videos. So here's how elimination method works. Now, mathematicians were not super inventive when it comes to naming things. So in solving systems by elimination method, we're trying to eliminate something. The something we're trying to eliminate is an entire variable. So in a system of linear equations, you have two equations, and each of those has two variables, an x and a y. The elimination method works in eliminating one of those variables completely from the system by adding stuff together in a really smart way. So here's what we're going to do. Number one, the setup is everything with elimination method. It's everything. What we want is we want to get all of our variables on one side, and we want our constant on the other side. So your x's and your y's are on usually the left-hand side, doesn't have to be the left, but on one side of your equation, and the constant is on the other side. So that's standard form. That's what I'm talking about in step number one. Get all your variables on one side and get your constant on the other side. I want to take a look at this as we go. So I want you to notice that that's the form we have right now. This is set up in standard form. We talked about it in the very beginning of linear equations. All our variables on the left, the number, their constant is on the right. That's what we're talking about. So also, while we're doing that, we really want to line up our variables. You're going to see this in the next few steps. We want to make sure x's are on top of x's and y's are on top of y's and constants are on top of constants, just like we have here. X term, that's great. Y term, that's fantastic. Constant, that's what we're talking about in step number one. And all the variables are on one side and our variables are in order. So y's and x's and constants are all lined up vertically is what we'd say. So step number two, after you have that, this is the hardest part right here, step number two. After you have that, we're going to look at the system and we're going to make sure that if we don't have this, we make it where we want one of the two terms, one of the pairs of terms, either our x's or our y's. It doesn't matter which one, but we want one of them to be identical with the exception of them having a different sign. So what I mean by that is I want either my x's to be exactly the same, one positive, one negative, or one negative, one positive, that's fine, or not both. Or I want my y's to be the same, but have different signs, plus minus or minus plus. I can't get both of them the same unless I have no solution or infinite solutions. So I'm not, hear that again, okay? Hear that again, I'll repeat it. I'm not trying to get both my x's and my y's the same at the same time. That would cause you a case to have infinite solution or no solution. I'm looking for just one of them. So I want to make sure that either my x's match up with different signs or my y's are exactly the same with different signs. It might take some multiplication here. So if you want a little side note, It might take you multiplying one or both equations by a number here to make that happen. We'll talk about that later in a future video. After that, here's how elimination works. It says, well, imagine this. Imagine you have all your variables lined up and your constant lined up, and you have one of them exactly the same, but the signs are different. Well, what happens when you add two things that are opposites? Same values, but different signs. They go away. They go away completely. They eliminate. That's what happens anytime you add opposites. And that's exactly what the elimination method plays off of. It says basically, set up your system so that you have two variables that are opposites. That way, when you add the entire system, that pair of variables that you matched up that have the same values with different signs is going to completely eliminate. Yes, it's going to leave you with one variable, but that's what you want. That's why we're not trying to get rid of both our variables at the same time. That'd be silly. We'd eliminate both of them. I'm not trying to do that. I'm trying to eliminate one variable out of my system so that I have only one variable remaining. With substitution method, we did that by taking one entire equation and replacing a variable with it. That eliminated that variable, left with this one variable. Watch the last video if you don't remember that. This is just a different way to go about it. In this way, we're more directly eliminated. We're not kind of going around and substituting to eliminate. We're literally adding them together and saying, you're adding opposites, it's going to be gone. It's fantastic. After that, once you've added this system, you're going to have only one variable left if you've done it right. After that, solve for the variable. It's going to be like one step. It's awesome. Once you solve for that one variable, you've completed. Now, don't lose track of this. What we're trying to do is we're trying to find the point of intersection. That's all these methods do. They find the point of intersection where two lines are going to cross, where two lines intersect. So once you solve for one variable, you've completed half of that point, either the x coordinate or the y coordinate. It doesn't matter which. So after you complete half your point, after you solve for the remaining variable, you have half your point. Just like the substitution method, you're going to take that half a point, plug it in to the appropriate variable, and it will allow you to solve for the other half of the point. If you find x here, you'll solve for y. If you find y here, you'll solve for x. You'll complete that half a point, so you have the whole exact point of intersection. That's kind of cool, without having to graph. The same exact way as substitution would do, but in some cases, elimination method is easier. We'll talk about that right now. So let's go ahead and let's work through two examples here real quick. The first one, I want to make sure we're on the same page here, because a lot of students ask me, they go, well, why are we learning this? Won't substitution method work? Yes, and in some of these cases, it wouldn't be too hard, but it's more cumbersome sometimes. So I want you to check that out here. If I wanted to do substitution, oh man, I hope you remember substitution method. Substitution method says solve for a variable. So already I'd be having an extra step in my problem. I'd probably solve this one and I'd solve it for y. So I'd be adding 2x. Once I did that with substitution, I hope this is ringing a bell. I hope this is in your head. You should have been studying that. I would have y equals 2x plus 4. I'd put that here. I'd have to distribute a negative, but I would be getting rid of that variable. I would be eliminating it through substitution. So I'd be eliminating the y variable, being left with an x variable only. I'd solve for x. I'd plug it back into my equation that I used to substitute. I complete my point. The elimination method does nothing different. However, when our systems are set up in a certain way, in other words, when our systems are set up that where all our variables are on the left-hand side already, this works pretty nice for elimination. So you're going to find out when you're going through your homework, some of the problems really lend themselves to substitution method if they're already solved for one variable. That's fantastic. Others lend themselves to elimination method when you're not solved for a variable. That's why we have two techniques, not to make your lives harder, but to make them easier so that we don't have to do extra work. So let's go through this and we'll see our steps work out for us. Number one, everything's lined up. I want my x's and my y's on one side, constant on the other. Same for the second equation. That's great. Also, I want to make sure that my x's are on top of x's. I want to make sure my y's are on top of y's. Constants are on top of constants. So this is looking pretty solid right now. Number two, this is the big one. I have to make sure that my equations have one pair of variables that are identical, with the exception of their signs. So they have to have different signs. X's don't cut it. That's 3x, that's 2x. They do have different signs, but I'm talking about the same exact coefficient with the exception of the sign being different. Our y's are what I'm looking at. Man, if you see this, this is a win right here. You're gonna love having variables that are identical with different signs already. So our step 2 is satisfied. I've lined it up. I got my x's on x's, I got my y's on y's, constants on constants, and I have one pair of variables that are identical, but they have different signs. Now here's the whole crux to the elimination method. When we add the system, and we're literally going to add it. When we add the system, well, 3x plus negative 2x. That's 3 plus negative 2. Well, that's positive 1x. What's negative y plus y? Negative y plus, well, isn't that 0? Yes, exactly. It's 0. That's exactly why we wanted this. Because if you add opposites, you're always getting 0. If it's your variable terms that you've changed into opposites, you're getting 0 of that variable. You're eliminating the variable. That's the whole nature of it. So line them up, make sure a pair of variables is the same with different signs, and when you add, that variable is going to eliminate. Now notice we don't want to eliminate both of them. We want one variable still. We're just trying to eliminate this variable. We get 0. Negative y plus y, remember think terms with the signs in front of them. Negative y plus y, that's 0. We don't even have to put the 0, but you've eliminated your y's. That's pretty darn cool. The constant on the other side, negative 5 plus 4, we're thinking carefully on that one, we're going to get negative 1. Whoa, wait a minute. X equals negative 1. You're halfway done. You've just completed half of your point of intersection. Remember, line, line. They're not parallel lines. They are going to intersect. Where they intersect is 1 comma something. So you've just solved for half of your point of intersection. That's kind of exciting. Now you got to solve for the other half. Here's, I mentioned this to you in substitution. I mentioned that one of the greatest things about substitution method was that when you solve for your variable, it's very easy to plug back in because you're already solved for the other variable. Elimination method is awesome because you don't have to do a lot of work in the beginning. It's all about setup. But when you plug in this negative 1, it doesn't matter which equation you use one of the equations, use whatever seems the easiest to you. For me personally, I don't like negative, so I'll use this one. But we're gonna have to plug in whatever variable we solve for. So we just found x. I know x is negative 1. So we're going to use one of these equations, it doesn't matter which. If you really, really want to check your work, use both. And make sure that when you plug in negative 1 here and negative 1 here, you get the same number for y. That will check your work. You don't have to do it if you don't want to, but that's a way to check your work. So I'm going to use my top equation. It doesn't matter which one. I'm going to plug in my negative x, or my negative 1 for x. When we solve it, be careful with your signs. If we add 3, and you know, I've been seeing this a lot lately. A lot of people are trying to leave me that as an answer. Is that a good answer? Go, oh, what's your y coordinate? Oh, my negative y coordinate is negative 2. Yeah, I don't really care about that. I don't care so much about that. I want to know what y is, not what negative y is. So we got to be careful with our signs. If we divide both sides by negative 1, negative 2 divided by negative 1 is positive 2. We now have completed our point of intersection. So here's what this whole thing says. Yes, there's 3 ways to solve systems of linear equations. One's graphing. Not very great because it's inefficient. It takes a long time. Number 2 is substitution. It's wonderful. When you have an equation that's solved for a variable already, it works great. When you don't, elimination method is our best friend. So the last 2 methods are what we use, but they all do the same thing. They find the point that is common to both lines. They find the one point in the universe where those 2 lines are going to intersect. That's exactly what that is. So eliminate a variable. It solves for one variable. Use it in either one of the lines, either one of the equations, to solve for the other half of your point, your missing variable. That's pretty much it. Now, I also made a big case about this. Check your work. Man, there's so many little mistakes that happen with signs and stuff. Just check your work real quick. Plug it in and make sure that this point is actually on both equations. What that means is if this point is common to both equations, it's common to both lines, there's only one point that does that, and it is the point of intersection. So we're going to plug that in. 3 times 1 Well, that's 3. Of course, if I get my sign right, that'd be helpful. 3 times -1 is -3. -2, well, that's -5. So I know that that's right. Notice how checking your work just saved me a bad answer. That's kind of interesting. Saved me a problem on a test if this was a test question, or a lot of confusion later. So plug this in here. -2 times -1, well, that's +2. +2 plus 2 is 4. So I caught a mistake. That's great. And I know that that's the right answer because that's the 1 point that's on both of my lines. That's it. Let's go into the next one. It doesn't always have to be the second variable that you eliminate. So I want to check out it doesn't have to be x's and y's. The next example, first thing I want you to notice about it, is it set up properly for elimination? So what I want for elimination method to work well, I want my variables on one side, I want them lined up vertically, and I want my constant on the other side. And that's what we have. I've got my m, my n, and a constant. My m, my n, and a constant. I have m's over m's, I have n's over n's, I have numbers over numbers. That's exactly what we want for elimination method. Now, could you do substitution method? Sure, but why would you? Because you'd probably solve for n, you'd have to subtract 2m or add n and subtract 5 or divide by a negative. And we all know that the more work that we do, the more chances for mistakes that we have. So substitution method, while it does work, we have a more elegant way to go around it. And it's not the easiest thing all of the time. It works all the time, but it's not the easiest thing all the time. So here, well, since I have this set up great for elimination, let's see if it works. Next thing, let's see. I want to make sure that one pair of my variables is exactly the same and has different signs. Here's 2m, here's -2m. This is what we're looking for. We're looking for opposites, guys, because if we have opposites and we add the system, those opposites are going to eliminate. That's the elimination method. It's wonderful. Notice the ends. Those are not the same. So I don't want both pairs of variables the same, but I want one of them. Now, I'll kind of preface the next video. What if you didn't know about that? Could you make the ends the same by multiplying? That's where we get in the next video. What if you don't, what if it's not like a gimme, like these are? That's already the same. That's fantastic. What if they're not the same? Then we'll start talking about how we multiply to make them the same. So we'll get there. So it's all on one side. My variables are lined up. It looks really good. I am looking at my m's right here. They're exactly the same with different signs. Let's go ahead and let's add. If we add the entire system, well, 2m plus -2m, that's 0. We just completely got rid of our m's. Are we going to get rid of our n's? Well, no. But when we add our m's and we get 0, it's leaving me with just one variable left, just with my n's. Basically, it's solving it for you. -n plus 3n is 2n. My constants, that's pretty easy to add. 5 plus -3, we're just literally vertically adding. We're going to get 2. This is how most of these work. Now, most of the time when you eliminate one variable, you have one variable left and you'll have to at most divide. So all we got to do is divide. N equals 1. Now, because we have some non-traditional variables like x and y, it doesn't really super matter what order we put those in because we're not given a graph. We don't really know what our horizontal axis is and what our vertical axis is. So we're going to kind of make an assumption that we're going to use m's in place of x's and n's in places of y's. So we'll consider that to be the last half of the point. So we basically solve for y here. Hopefully it makes sense to you. We got it lined up, we added it, we had opposite variable terms. That adds to 0. We have non-opposite variable terms. It leaves you with one variable to solve for. It's really easy to solve, just divide, and then you have half your point. Now, are we done? Well, not really. I mean, we did half of it, but now we have to solve for the missing half. We have to solve for our m. This is again, the downfall of the elimination method is it's not super obvious which equation to use because there's no really good choice some of the times. You can use either one. It does not matter, but you are going to have to do a little bit more work here. So let's solve, I just use this one, the top one. So let's use the top equation. Coming from that 2m minus n equals 5, if we know that n is 1, well, that allows us to solve for the missing variable of m. So yeah, there's a little bit more work than solving for the variable in substitution because you haven't done that work ahead of time. Notice what I'm saying here. Substitution method solves for a variable first and uses that substitution to eliminate a variable by substitution. Elimination method does it backwards. It eliminates the variable, and then you have to solve for a variable later. So substitution method solves first, eliminates second. Elimination method eliminates first, solves second. Same idea, just a different order. So if we solve for m, we complete the other half our point. So we got the point 3, 1 where those two lines are going to intersect. Let's check it. If I plug in 3 for m and 1 for n, so remember we wrote this as m comma n. We'd have 2 times 3, let's see, that's 6. 6 minus 1 is 5. Okay, I know for a fact this point is on that line. Now we try the other one because trying 1 is not good enough. We have to have this point on both of our lines. It's got to be common to both. Negative 2 times 3, that's negative 6. Negative 6 plus 3 times 1, that's 3. That's negative 3. Okay, now I'm assured of victory on this problem right now. I know that point is common to both of these equations. That means it's on both the lines, and a point that's common on both the lines has to be at an intersection, or the lines were exactly the same. That's not the case because we would have eliminated all our variables in those cases. So this is the point of intersection of those two lines. I hope this is making sense. We're going to do one more example right now, and I'm going to start gearing you to the next videos where we deal with some more complicated ideas. This video is just to get your feet wet, just to make sure that you understand, look, you got to have your variables on one side for this to work. You got to have them in order, x's, y's, constants. You got to have one pair of variables that's identical, but different signs. That means opposite terms. So we want some opposite terms. That way when we add the system, those terms disappear. They eliminate. We're left with one variable. We can solve it, and then we can use either equation to solve back for the missing variable. The one that we eliminated is the one that you're going to solve for. That should make some sense. So I'm going to erase this. I'm going to put one more up on the board. If you'd like to give it a try, right after I write it, go for it. See if you can do what these things are. I think you can. Something should be jumping out at you on this problem when you're looking at it and I ask you, what are we dealing with? That's probably a good choice to start. What are we dealing with? You know, it's a system. You got two linear equations. System of linear equations. Fantastic. What's the best method to use? Let's go through that real quick, shall we? Would you want to graph it? Would you really want to graph that? Intercept method? That sucks. Because that's some fractions or decimals. Solving for y here, not super fun. That's also some fractions. So graphing method, I don't want to do that. How about substitution method? Would you want to do substitution method? Because notice, you're going to have to solve one of these equations for one of the variables. And it's going to start getting pretty nasty pretty darn fast. So thank goodness we have a different method. Because otherwise, graphing would turn into a complete, man, it'd be a disaster. We'd have fractions everywhere. We're not sure exactly where our lines cross unless we're using like a computer program. Substitution method, it's very doable. I mean, you could do it, but you're going to have a lot of fractions floating around. That's not always a great choice. So elimination method says, let's go a different route. Let's make sure that our variables are on one side. Are they? Yeah, they look great. I get x, y number, I get y, x number, but there's something that you should have been kind of thinking as I've been talking. They're not lined up. So in order to eliminate variables, we really do want these variable terms lined up vertically. So this one's fine, this one's not so hot. So I'm going to rewrite this. As we're rewriting, make sure that our terms go with the signs in front of them. So our plus 7x translates to a positive 7x, and our negative 6y is a minus 6y. Our constant doesn't change. That looks a whole lot better. We got variables on top of the same identical variables. So we have x's on x's, y's on y's, we got constants on top of constants. It's looking pretty good. Now we're trying to identify if we have one pair of variables that are opposite terms. So same look, different sign, opposite terms here. X's don't do it, but we notice right away that the y's do. do it. We got 6y, we got minus 6y. That's perfect. That's exactly what we want. Man, good thing we didn't do substitution, right? Because that's a whole lot more work. So once we have identified that, variables are lined up. We have one pair of terms that are opposite terms, so same terms, different signs. When we add that, every time you add opposite numbers or opposite terms, you get 0, and this is no exception. Our x's add to 9x, our y's add to 0. You don't even have to put anything. You can, I guess, you can put plus 0, but 6y minus 6y is 0 for any value of y. That's great. On the right-hand side, get your signs right. It's really common when people are doing elimination method to mess their signs up. It's so easy to do. It's so easy to go, oh yeah, -1. Because you're going so fast, you're not thinking of addition rule. We got to be real careful on this stuff. So -5 plus -4, that's like adding debt. -5, owing $5, plus a debt of 4, so plus a debt of $4, you're going to owe $9 here. Notice what it did. Simply lining this up as x's, y's numbers makes this a lot easier to work with. It lets you identify very easily that you already have a pair of terms that are opposite. That's great. So when we add our system, 9x, great. -9, fantastic. Just one step. And we complete half of our point of intersection. These are two lines, they're going to intersect. And I know that half of that is, well, an x-coordinate of -1. Now, we're almost done. All we got to do now is pick one of these. It doesn't matter which one you pick. So I would pick the one that has less negatives. I'd pick this one in it because I don't have to deal with the minus. That's the only reason why I'm picking it. It does not matter. So I'm going to rewrite it, though, just to make sure that I'm not accidentally plugging it into, well, you know, kind of thinking this one but accidentally using this one. It happens to me sometimes. I switch numbers. So I'm going to pick this one, write it down again. And if we substitute in an x-coordinate of -1, now we solve it. You know, it's okay to get fractions here. They're a little harder to check, but it's fine to get fractions. We just completed our point. We completed the point of intersection. The one point in the world that needs to be common to both these lines is the point of intersection, and it needs to occur at -1, -1/2, and we're certainly going to check our work. So let's plug that into our original. Let's plug in -1 for x and -1/2 for y. So if we plug in -1 for x, well, that's -2. If we plug in -1/2 for 6, it cuts it in half and it changes the sign. That's plus -3. That's -5. So I know that this point is at least on this line. It also has to be on this line, so we're going to try that. So we kind of switch these. So -1/2 for 6. Well, that's -6 times -1/2. So that's going to cut it in half and change the sign. That's +3. But if I plug in -1 for x, that's -7. So 3 plus -7, that's -4. Oh, that's fantastic. I know, it's on both lines. And that therefore verifies that that is the point of intersection. That solves the system of linear equations. So your big takeaway here, this is the last of 3 methods that we have to solve systems of linear equations. First one's graphing. It's honestly just used to get you in the door, to show you what we're trying to accomplish. We're trying to find out where the lines cross, that one point of intersection. Substitution method is awesome if you have one equation solved for one variable already. If not, elimination method is typically your best bet. That's usually the way it works. If the equation is easy to solve for a variable, you might go ahead and do substitution, but when it's not, man, we don't want to mess around with that. Elimination method steps in and gets it done. So that's all elimination method really is. Next video, I'm going to show you how to multiply to make this happen, to basically force this to happen, to force opposite terms. It takes a little bit of thought. It's going to be related to common denominators, actually. So I'll see you for the next video. Study this stuff up a little bit. Be very good at elimination method when your variables are opposite terms already, and then I can get you going on the next one. Okay, guys, have a great day.